Welcome to the SAR channel, where sound and audio are demystified. Linear pulse code modulation, PCM, is accurate, but wastes a lot of data. Since it needs a large number of bits, PCM isn't practical for many audio uses. Reducing the bit rate is important because it makes digital audio and video possible in many new areas. To meet this need, audio engineers have created a wide range of lossy and lossless codecs. Even though perceptual codecs have a short history, several key methods were created early on and inspired the development of more advanced systems. Because the field evolved quickly, most early codecs are no longer in use, but they built the foundation for today's standards. MUSICAM, masking pattern adapted universal subband integrated coding and multiplexing, based on MASCAM, masking pattern adapted subband coding and multiplexing, was one of the first perceptual coding methods. It reduced data size using subband analysis and psychoacoustic models. Other examples include OCF, optimal coding in the frequency domain, and PXFM, perceptual transform coding, which use similar transform-based approaches. ASPEC, audio spectral perceptual entropy coding, was another standard that used the MDCT transform. It was more complex but could compress audio effectively for low bitrate uses, such as ISDN. In 1988, the International Organization for Standardization, ISO, and the International Electrotechnical Commission, IEC, created the Moving Picture Experts Group, MPEG, to develop methods for reducing audio and video data. The first standard, completed in November 1992, became known as MPEG-1 and was the first global standard for perceptual coding of high-quality audio. MPEG-1 was originally designed to handle both audio and video within the bandwidth of a CD. It supports different bit rates and can encode mono, dual mono, and stereo audio. In joint stereo mode, it can also reduce the bit rate by removing unnecessary or repeated stereo information. MPEG-2 built upon MPEG-1 by keeping its 3 audio layers and adding new features, mainly surround sound. MPEG-2 players can play MPEG-1 audio, and MPEG-1 2-channel players can still decode the stereo parts of MPEG-2 surround files. In an MPEG bitstream, audio data is sent in frames. Each frame can be decoded on its own. The size of each frame varies depending on the MPEG layer and the specific coding method used. MPEG-1 Layer I is a simpler version of the MUSICAM system. It's a subband codec made to deliver high-quality sound with low processing needs, but it uses a high bit rate. A polyphase filter splits the full audio signal into 32 equal-width subbands. The filter is critically sampled, meaning it keeps the same number of samples as the original signal. Since the subbands overlap, one frequency can affect 2 bands. The filter isn't perfect, but its error is very small. Although all subbands are equal in width, the ear's critical bands aren't, so the bit allocation system adjusts for this by giving more bits to lower frequencies for better quality. Like other perceptual coders, MPEG-1 Layer I uses how the ear hears, especially masking effects, to make the sound seem identical to the original. The decoder is inexpensive because it doesn't perform psychoacoustic analysis or bit allocation. It's also compatible with better encoders. If encoding improves, so does sound quality. Since encoding depends on digital signal processing, it allows more advanced coding methods to be developed. The MPEG-1 Layer II codec is basically the same as the original MUSICAM system with slightly different frame headers. It's similar to Layer I but has a more advanced design. It offers high-quality sound with slightly more processing and works well at moderate bit rates. Like Layer I, it is a subband codec. Decoding in Layer II is still simple. The decoder just unpacks the data frames and sends them to the reconstruction filter. Layer 2 can also use stereo intensity coding and includes dynamic range control to adjust to different listening environments. It uses fixed-length data words and is commonly used in digital audio broadcasting (DAB) and digital video broadcasting (DVB). The MPEG-1 Layer III codec, known as MP3, is based on the ASPEC system and includes parts of MUSICAM, such as a sub-band filter bank, to stay compatible with layers 1 and 2. Unlike those layers, Layer III is a transform codec, making it more complex but able to keep good sound quality even at low bit rates. Layer 3 offers high-frequency resolution but lower time resolution, which can cause pre-echo effects when quantization errors spread across the time window. To reduce this, the MDCT window can switch between time and frequency focus based on psychoacoustic analysis. MP3 files can be encoded at many different bit rates, but the format isn't scalable for variable decoding. This means the decoder can't pick smaller parts of the data stream to produce lower or higher quality versions of the same audio. In the Layer 3 encoder, bit allocation is handled through dynamic quantization. Instead of assigning bits directly from signal-to-noise ratio (SNR) values, the encoder uses a noise allocation loop that determines how much quantization noise each subband can have. This process automatically decides how bits are distributed. Inside this system, an inner rate loop works to lower the data rate. Huffman coding assigns shorter codes to smaller, more common quantized values. If the bit rate becomes too high, the rate loop increases the quantization step size, producing smaller values, shorter Huffman codes, and a lower bit rate. Quantizing the spectral data and applying Huffman codes can take time. An outer noise control loop evaluates how much quantization noise appears in the reconstructed signal. It adjusts the quantizer step size so that noise stays below the masking threshold in each frequency band. If noise in any band goes above that level, the scale factor is adjusted to reduce it, and the loop repeats the calculation. Ideally, this results in quantization noise that is inaudible. The bitrate in Layer 3 can change from frame to frame, allowing variable bitrate VBR recording. The psychoacoustic model determines how many bits are needed for each frame. Sometimes a codec's output file is a different size or slightly longer than the original due to processing blocks, delays, and look-ahead functions. To keep the same file length and time alignment, some codecs include extra data in the bit stream, called original file length, OFL, which marks how many samples to trim at the beginning and end. To reduce redundant data between stereo channels and make use of how humans perceive sound direction, Layer 3 offers 4 stereo coding options. Normal stereo, separate left and right channels. MS stereo, the whole signal coded as middle and side. Intensity stereo, low frequencies coded as left-right and high frequencies as intensity. And a mix of MS and intensity stereo, low frequencies as MS, high as intensity. Each frame can use a different mode. Layer 3 includes both MS, mid-side, and intensity stereo methods. In MS coding, parts of the left and right channels are combined into some mid and different side signals before quantization. This prevents unwanted stereo effects and saves bits when the channels are similar. In intensity stereo coding, the higher frequencies of both channels are combined into one summed signal. Left and right scale factors are then added to position the sound in the stereo field. This keeps one frequency shape for both channels but adjusts their levels. It works well for steady sounds but not for short, changing ones, which can cause stereo image distortion. Intensity stereo coding is mostly used at low bit rates. MP3 files can be played using either hardware chips or software decoders. To make decoding faster and reduce processing power, some software decoders include special optimizations. The most demanding part of decoding is calculating the hybrid synthesis filter bank. This process can be simplified by mixing stereo channels into mono in the frequency domain before filtering, so only one filter operation is needed. The downmix can be done by taking a weighted sum of the left and right channels. Even more efficiently, Built-in routines can compute the sum only for the scale factor bands that use left-right stereo. For MS and intensity-coded bands, only simple scaling is required. If you've enjoyed this video so far, please hit the subscribe button for more. Thank you. The MPEG-1 standard includes two psychoacoustic models used to find the minimum masking threshold below which sounds become inaudible. These models are optional and used only in the encoder. The difference between the loudest signal and the masking threshold helps the bit allocator set quantization levels. Usually, Model 1 is used for layers 1 and 2, while Model 2 is used for layer 3. Psychoacoustic Model 1 offers a simple way to analyze the spectrum and produce signal-to-mask ratios. It performs these 9 steps. 1. Run an FFT analysis. 2. Measure the sound pressure level. 3. Account for the threshold of hearing in silence. 4. Identify tonal and non-tonal elements. 5. Reduce the number of tonal and non-tonal maskers. 6. Calculate each masker's threshold. 7. Compute the overall masking threshold. 8. Find the minimum masking threshold. 9. Determine the signal-to-mask ratio. Model 1 groups all non-tonal sounds within a critical band into one value at one frequency. This works well for low frequencies where subbands and critical bands align, but is less effective at high frequencies, where one subband may contain several critical bands. As a result, high-frequency subbands might not get accurate non-tonal analysis. Psychoacoustic Model 2 performs a more detailed analysis than Model 1, but requires more processing power. It is designed for lower bit rates and produces a signal-to-mask ratio for each subband, just like Model 1, but with a different and more accurate approach. It models the noise floor of the signal using many spectral points instead of broad subbands and includes an unpredictability measure to detect tonal and non-tonal elements. Model 2 includes these 14 steps. 1. Rebuild input samples. 2. Compute the complex spectrum. 3. Predict magnitude and phase. 4. Calculate unpredictability. 5. Measure energy and unpredictability in each partition. 6. Apply the spreading function to both values. 7. Derive the tonality index. 8. Determine the needed signal-to-noise ratio. 9. Calculate power ratio. 10. Compute energy threshold. 11. Spread the threshold energy. 12. Calculate the final audibility threshold. 13. Apply pre-echo control. 14. Compute signal-to-mask ratios. Since Model 2 was published, newer and improved methods have been developed. Therefore, most modern encoders use enhanced versions of this model. An encoder that follows the original version exactly will not perform as well as these updated implementations. The MPEG-2 audio standard was created for uses ranging from internet downloads to high-definition digital TV, HDTV. It supports multi-channel sound in a backward-compatible way, and includes both a low sampling rate option and a non-compatible multi-channel format, called Advanced Audio Coding AAC. MPEG-2 builds on the MPEG-1 audio standard, keeping the same encoding and decoding methods for layers 1, 2, and 3. In most cases, the same layer algorithms used in MPEG-1 also work for MPEG-2. Multi-channel MPEG-2 audio is backward compatible, meaning an MPEG-2 decoder can play MPEG-1 files, and an MPEG-1 decoder can extract stereo sound from an MPEG-2 file. However, MPEG-2 also allows the use of new, non-compatible codecs. A wide range of bit rates, quality levels, and layer options in MPEG make it suitable for many uses, including computer multimedia, CD-ROMs, DVDs, computer storage, networks, studio recording, ISDN transmission, digital broadcasting, and multi-channel TV. Many C and C++ programs for MPEG-1 and MPEG-2 audio coding and decoding are available online for personal computers. The backward-compatible Layer II format is used for some DVD video soundtracks, though its matrix surround sound method doesn't keep spatial accuracy as well as discrete channel coding. The MPEG-2 Advanced Audio Coding (AAC) format can handle mono, stereo, or multi-channel audio with up to 48 channels, including 5.1 surround sound at different bit rates. It delivers high-quality sound even at low bit rates. AAC is also the main audio format used in MPEG-4 for high-quality audio coding and can support lossless compression. MPEG-2 AAC is not backward compatible with MPEG-1, meaning an MPEG-1 decoder cannot play AAC files. To balance audio quality and processing power, AAC offers three profiles: main, scalable sample rate, and low complexity. In the AAC codec, predictive coding analyzes each block of frequency coefficients. For sudden or short sounds, transients, this produces a smoother spectrum, helping identify and code these sounds more efficiently. By studying the spectral data from the MDCT, Temporal Noise Shaping (TNS) controls how quantization noise spreads over time, shaping it so it's less noticeable to the ear. Using the relationship between time and frequency domains, TNS improves prediction accuracy. In time domain coding, noise follows the input signal's frequency pattern. In frequency domain coding, noise follows the input signal's time pattern. TNS makes the noise follow the shape of the transient, hiding it beneath the sound and reducing unwanted pre-echo effects. Importantly, TNS prediction happens across frequency, not time, so the resulting noise is shaped in time, not in frequency. This boosts time resolution and reduces how much the noise spreads out over time. In short, TNS lets the encoder control pre-echo noise inside each window so it's masked by the actual sound. TNS improves coding for both transients and pitch-based sounds like speech. Speech impulses are often hard to compress efficiently and can cause sudden spikes in bitrate. TNS reduces these spikes and pre-echo artifacts. It also lets the codec use longer transform blocks more often without adding distortion and works better at low sampling rates. TNS dynamically adjusts between high time resolution for quick sounds and high frequency resolution for steady sounds, doing this more efficiently than switching windows. The TNS filter can target specific frequency ranges using predictive coding like DPCM. One filter can shape the whole spectrum, or different filters can handle different parts, while some frequencies may skip TNS altogether, allowing flexible frequency-dependent noise control. AAC uses two main stereo coding methods, intensity coding and MS mid-side coding. These methods can be combined and applied to specific parts of the signal's spectrum. MS coding is used for channel pairs placed symmetrically to the left and right of the listener, helping prevent spatial unmasking. It can be switched selectively over time, block by block, and across frequencies, scale factor bands. MS coding also separates the placement of coding noise from the masking signal, which preserves high-frequency details in transient sounds. Intensity stereo coding works on the principle that high-frequency perception depends on energy-time envelopes. Some signals can be shared between channels using one set of spectral values, while envelope information is maintained for each channel. Intensity coding can be applied between channel pairs or across coupling channels, where spectra are shared and additional audio elements, like a voiceover, can be mixed in. Both MS and intensity coding can be used for stereo as well as 5.1 multi-channel audio. Adaptive Transform Acoustic Coding algorithm was originally developed for the SDDS cinema sound system and later used in formats like minidisc to reduce audio data size. An ATRAC encoder takes digital audio input and splits it into blocks. The signal is divided into 3 subbands and converted into the frequency domain using variable block lengths. Unlike some codecs, ATRAC applies psychoacoustic principles to both bit allocation and time frequency splitting, combining subband and transform coding techniques. The block length adapts to the audio signal, changing amplitude and time resolution for steady or transient passages. The encoding process can be divided into 3 parts: time frequency analysis, bit allocation, and quantization of spectral components. Transform coders must balance frequency and time resolution. Long blocks give high frequency resolution, which works well for steady signals, but can spread quantization noise over time for transients, causing pre-echo. ATRAC avoids this by using adaptive block lengths, long mode for steady signals, narrow frequency bands, and short mode for transients, wider bands, better time resolution. Transient attacks shorten blocks, while slow-changing signals lengthen them. Time splitting also uses backward masking, where nearby tones mask each other. In long mode, frequency resolution is good, but noise from transients can be heard. Switching to short mode limits noise duration, letting pre-masking hide it. Post-masking in long mode masks signal decay. Each subband can choose its own block size. Low frequencies may use long blocks, mid and high frequencies may use short blocks. The Perceptual Audio Coding codec was created to handle audio at bit rates from 6 kilobits per second for mono up to 1024 kilobits per second for 5.1 channel surround sound. It was mainly designed for digital audio broadcasting and internet downloads offering near CD quality and FM quality sound. PAC's encoder design is similar to other perceptual codecs. Its model for coding mono signals is based on MPEG-1 Psychoacoustic Model 2. Additionally, PAC uses unequal error protection, UEP, to give stronger protection to more important parts of the audio data. If you've learned anything new so far, please like the video. It really helps the channel grow. Thank you. The AC3 Dolby Digital codec is widely used for multi-channel audio in applications like digital TV, DTV, satellite TV, DBS, DVD video, and Blu-ray. It was developed after the earlier AC1 and AC2 codecs. AC1, Audio Coding 1, is a stereo codec that uses adaptive delta modulation and analog companding. It is not a perceptual codec and was used for satellite TV, FM relays, and cable radio. The AC2 is a set of 4 single-channel codecs designed for 2-channel or multi-channel use, mainly for point-to-point transmission. It has been used in PC sound cards, studio/transmitter links, and ISDN connections for long-distance recording. The AC2 Bitstream is designed to be resistant to errors. The AC3 codec, commonly called Dolby Digital, evolved from AC2 and commercial cinema applications. It is widely used for 5.1 multi-channel surround sound, including left, center, right, left surround, and an LFE subwoofer channel. The AC3 is backward compatible with matrix surround, 2-channel stereo, and mono playback, all of which can be decoded from the same bit stream. Unlike matrixed 5.1 formats, AC3 keeps channels discrete to prevent quantization noise from affecting the wrong channel. The decoder can digitally downmix the multi-channel stream to produce the desired output format. AC3 includes dialogue normalization, which keeps the volume of speech consistent across programs and channels, and dynamic range control, allowing the listener to adjust the program's loudness range. Downmixing is also supported, enabling a multi-channel recording to be reduced to stereo or mono with inter-channel levels set by the mixing engineer. By removing redundancies between channels, AC3 achieves higher coding efficiency than AC2. AC3 uses hybrid backward/forward adaptive bit allocation in both the encoder and decoder. Data reduction is achieved by quantizing the audio in the frequency domain. The encoder converts time domain PCM samples into frequency domain coefficients using an analysis filter bank. Each coefficient is represented by a binary exponent and mantissa. Groups of exponents form the spectral envelope, which guides how many bits are allocated to each mantissa. The spectral envelope and mantissas for 6 audio blocks are packaged into a frame for transmission. Decoding reverses the process. The decoder synchronizes the bit stream, checks for errors, and extracts the spectral envelope and mantissas. The bit allocation info is used to dequantize the mantisas, and the spectral envelope is decoded to recover the exponents. These are transformed back to the time domain to produce PCM audio samples. The AC3 encoder is complex, using dynamic optimization and combining differential exponents into groups for better bit efficiency. A key feature of AC3 coding is its ability to compress multiple audio channels into a single low bitrate stream efficiently. To improve bit efficiency, the encoder can use channel coupling and selective rematrixing on certain frequencies while maintaining accurate spatial perception of the sound. AC3 audio data is organized into frames, with each frame encoded independently. AC3 algorithms can run on general-purpose or high-performance dedicated processors. Both floating-point and fixed-point processors are used. Floating-point processors are usually more expensive but can process AC3 faster and with high fidelity. Fixed-point processors are often more cost-effective due to lower price and memory needs. In some cases, real-time encoding on a PC is handled using a DSP plugin system. AC3, widely known as Dolby Digital, is used in many applications. In movies, it provides 5.1 surround sound for theatrical releases. Dolby Digital Plus, also called Enhanced AC3 or EAC3, is an extended format. It adds spectral coding for low bit rates, supports up to 7.1 channels, and allows higher bit rates. Dolby True HD is a lossless extension that builds on Dolby Digital and uses Meridian Lossless Packing MLP for lossless audio. It supports up to 24-bit depth and 192 kHz sampling with multi-channel streams including lossless downmixes. In consumer use, Dolby Digital encodes 5.1 channels or fewer for cable, satellite, DVDs, Blu-ray discs, and is an optional format for DVD audio. It is also used for the audio in ATSC digital television. Dolby E is a professional codec that transmits up to 8 audio channels plus metadata over a single AES-3 interface. This allows a 5.1 mix to be carried and recorded on 2-channel media. The DTS Digital Theater Systems Codec, also called Coherent Acoustics, is used to encode multi-channel audio in various setups. It uses a subband approach with adaptive differential pulse code modulation, ADPCM, to compress time-domain audio data. The DTS version for commercial movie soundtracks differs from the version used in consumer products. Many lossy audio codecs exist for different purposes. Some follow standards like MPEG, while others do not. Ogg Vorbis is an example of a free, open-source, royalty-free codec that provides good quality lossy compression. Meridian Lossless Packing, MLP, is a proprietary audio codec designed for lossless compression, used in formats like DVD audio and Blu-ray. MLP reduces average and peak data rates, saving storage and bandwidth, while keeping the audio identical to the original signal. Unlike lossy codecs, it does not discard any data, though its compression is less than lossy methods and depends on the audio content. The output bit rate can vary with the signal, but a fixed rate mode is also available. MLP supports all standard sampling rates and bit depths from 16 to 24 bits, and can encode stereo and multi-channel audio simultaneously. It only accepts PCM audio data, not video, text, or low-bit signals. By packing the data efficiently, MLP ensures exact bit-for-bit accuracy, avoiding errors that can occur with PCM through generation loss or transmission. Proprietary check data is included in the bitstream so the decoder can verify accuracy, making it robust against disk or broadcast errors. The MLP bitstream carries compressed audio plus instructions for the decoder about sampling rate, bit depth, channel setup, and other parameters. It can also include auxiliary data like speaker source info, copyright and watermark info, and error checking data. To achieve a fixed bit rate, MLP can use a single-pass process if the target is moderate, or a 2-pass process for rates near the compression limit. Fixed rates give predictable file sizes, support video, and maintain compatibility with interfaces. MLP is used optionally on DVD audio and Blu-ray discs, providing high-quality, lossless multi-channel audio with efficient storage and reliable playback. Several other lossless audio codecs have been created. These include FLAC, Free Lossless Audio Codec, LRC, Lossless Real-Time Coding, Monkey's Audio, WavePack, LPAC, Shorten, OptiFrog, DirectStream Digital DSD used in SACD, WMA, Windows Media Audio, and ALS Audio Lossless Coding. Thank you for watching till the end. To better understand each video, make sure to watch the previous ones. Some may serve as prerequisites for the next. If you have any questions or opinions, feel free to leave a comment. Until next time, subscribe and stay curious.